Hello. So, in the last class, I was discussing double refraction. So, next is types of uniaxial crystals. So, next is types of uniaxial crystals. Uniaxial crystals. Uniaxial crystals means doubly refracting crystals. So, two type of doubly refracting uniaxial crystals are. One is called as positive, another is called as negative. So two type of crystals are there. One are called as positive crystals and another are known as negative crystals. So what is the meaning of positive crystal and negative crystal? So one is positive crystal. Can anyone tell me what is positive crystal and what is negative crystal? How will you define positive and negative crystals? Negative crystals. So try to understand one thing, that before defining positive and negative crystal, try to understand if you are having a point source. You have placed a point source in the air. Where you have placed it, this is the point source in the air. So it will emit light and this light will propagate in all possible direction with the speed c. Okay, with the same speed it is going to travel in all the directions. So what type of wavefront will emerge from it? This will be spherical wavefronts will emit. So it is going to emit spherical wavefronts like this. Okay. So this is a point source in air. This is a point source. This is a point source. And this point source is emitting spherical wavefronts. They are spherical wavefronts. Wavefronts. This is one thing. Now, second is when we are having doubly refracting crystal, if this is a doubly refracting crystal on this side and light is incident on it, okay, then what is going to happen here? You will have two plane polarized lights. ठीक है ना? You are going to have two plane polarized light in doubly refracting medium. So if you are having a point source, if you are having a point source inside a doubly refracting crystal, then what you are going to find out, there will be two wavefronts. ठीक है ना? Two wavefronts, they are going to be emerged from a single point source if point source is placed in a doubly refracting crystal. I'm telling you one thing, if you are having a point source on a white paper, take a white paper, make a point source here. Take a point source, you can make a dark point here with the pen and then place a doubly refracting crystal here. ठीक है ना? Place over it a doubly refracting medium or crystal and then observe this from the outside. What you are going to find out, you are going to observe there are 2 points. So if you are looking at this dotted point which you have created on the white paper and you are looking at this point, dotted point, through the doubly refracting crystal, then in place of 1 point you are going to observe 2 points. 1 point will be corresponding to Ore ordinary light and second is corresponding to extraordinary light. Now if you start rotating this crystal like this, then what you are going to find out, that one of the point will be fixed and another point that is going to be rotating about this fixed point. So this fixed point is corresponding to Ore. Okay, this is corresponding to Ore and this is corresponding the point which is moving around this fixed point. That point is corresponding to E ray. So when you have placed a point source below the doubly refracting crystal, so whatever light is emerging from that light is of two types. ठीक है ना? That light is split into two types. One is ordinary ray, another is extraordinary ray. So ordinary ray behaves very similar as we have studied up to this point. So this point, that fixed point, it will be there. But if you start rotating this doubly refracting crystal, what you will find out that the extraordinary ray, ठीक है ना, that is emerging from this point, that is going to rotate about this point in this way. So 2 points you are going to observe for a single point you have made on the white paper. ठीक है. So basically for a from a source, from a point source, two type of lights you are getting. One is ordinary light, another is extraordinary light when light enters into a doubly refracting medium. Now here, so one will be here E ray, another will be O ray like this. So what will happen if you are having a point source like this, not in air but in doubly refracting medium? In doubly refracting medium, if you place a point source, then what will happen? Okay. So to explain what type of wavefront is are going to emerge, try to understand one thing, that these crystals, these doubly refracting crystals, they can be of two types. They can be of two types. One is known as positive crystal, another is known as negative crystal. So example of positive crystal is quartz. It is quartz. So in quartz crystal, what happens? Velocity of the ordinary light. What is VO? Velocity of the ordinary light. It is greater than velocity of extraordinary light in general. So speed of ordinary light is greater than speed of extraordinary light in general. But when light will propagate along the optic axis, both VO and VE, they will be equal. So except optic axis, in all other directions, VO will be greater than VE. So that type of crystal in which speed of the ordinary light is greater than the speed of extraordinary light. Speed of the ordinary light is greater than speed of the extraordinary light. They are known as positive crystal. They are known as positive crystal. Now you are aware that speed of light in a medium V, that is given by C upon N. N is the refractive index. N is refractive index of the medium. So how you define refractive index? Refractive index N is equal to C upon V. So what is the velocity of the light in a medium? That will be C upon N. So try to understand what will be VO. VO will be C upon refractive index of ordinary light in the doubly refracting medium like quartz. That will be greater than the C upon Ne. ठीक है. So Ne is greater than No here. So I can write here, it means Ne is less. Sorry, I'll write here No. This No is less as compared to Ne. This will be. So this type of crystals in which speed of the ordinary light is greater than speed of the extraordinary light, they are known as positive crystal. An example is quartz. An example is quartz here. Now try to understand what you are saying. So if you are placing a point source, try to understand. So this is a point source here. Okay. So you have placed this inside the quartz. So this is a point source which we have placed in the, I can make here on this side. So you place this point source inside the quartz medium. So whatever light will emerge, that emerged light, ठीक है ना, it will make two wavefronts. One wavefront will be corresponding to ordinary light, another will be for extraordinary light. And these wavefronts, they will be different from each other because they are traveling with different speeds in the medium. Now what you are saying, VO, ordinary light, its velocity of ordinary light is greater than velocity of extraordinary light. Can you tell me one thing? What type of wavefront will be there corresponding to ordinary light? What is the property of ordinary light? Ordinary light is that light. Ordinary light is that plane polarized light which travels with the same speed in all possible directions. So you are saying ordinary light is traveling with the same speed in all possible directions. So what type of wavefront of ordinary light that will emerge from this point source, that will be spherical. So you are going to get this type of spherical wavefront. that will emerge from the source, from the point source. So this is the wavefront corresponding to ordinary light. So this is corresponding to ordinary light. This is the wavefront. Why? It is spherical because ordinary light, it travels with the same speed in all possible directions. Next, there will be a direction corresponding to optic axis. So if I assume, suppose this direction is optic axis, or you can say this is optic axis. Suppose this is X, you can choose anywhere. You can choose either X or Y. This is your choice. So I'm saying this X direction, this is the direction of optic axis. This is the direction of optic axis. So what you are saying, what is the direction? What is the meaning of optic axis? From the optic axis discussion, we know that both ordinary light and extraordinary light, they travel with the same speed. They travel with the same speed along the optic axis. So try to understand the wavefront of ordinary light and extraordinary light. They are going to touch here. They are going to touch each other along the optic axis. Along the optic axis, both O ray and E ray, they are traveling. They are going to travel with the same speed. So both the wavefronts, they will touch because along the optic axis, they are traveling equal distances in equal time. So both the wavefronts, they will touch each other along the optic axis. In other directions, the speed of E ray, extraordinary ray, is less. So in other, except this optic axis, in other direction, it will lag behind. This will left behind. So this will be the this type of wavefront you are going to find out. So this type of wavefront will be for E ray. So this is the wavefront for E ray. E ray. So try to understand along the optic axis they are traveling with the same speed. They are traveling with the same speed. So that's why they are touching both the wavefronts. They are touching each other. But in other directions, you will find out that speed of E ray is less as compared to ordinary light. Okay, so this type of wavefront will be there for E ray. So for E ray, there is ellipsoidal. What type of wavefront E ray is exhibiting? That is ellipsoidal. And what type of wavefront is exhibited by the ordinary light? That is spherical. So here you can write O ray. ठीक है ना? They have what type of wavefront these O ray have? They have spherical wavefronts. They are going to have spherical wavefronts. Wavefronts. While these E rays, they are going to have ellipsoidal. They are going to have ellipsoidal wavefronts. They are having ellipsoidal wavefronts. So O ray and E ray. So this type of wavefronts they are going to exhibit. Remember this thing. Is it clear? So you can write here, in case of positive crystal, you can write please, in case of positive crystals, in case of positive crystals, so I think this is outside the board, no? Now it's okay. Inside the positive crystal, ellipsoidal wavefront, of E ray, ellipsoidal wavefront of E ray, ellipsoidal wavefront of E ray will lie, ellipsoidal wavefront of E ray will lie inside the spherical wavefront, inside the spherical wavefront, inside the spherical wavefront of ordinary light, inside the spherical wavefront of ordinary light. So this type of crystals where speed of ordinary light is greater than speed of extraordinary light, they are known as positive crystal. Best example is quartz. This is first type of crystal. Second type of crystal are negative crystals. Here example is calcite. Here calcite. So calcite crystal, they are negative crystals. So what are negative crystals? Negative crystals are those crystals in which velocity of ordinary light is less as compared to velocity of the extraordinary light. In terms of refractive index of the medium with respect to E ray and O ray, you can say that refractive index of O ray is greater than the refractive index of extraordinary ray. So this type of crystals in which speed of ordinary light is less as compared to the speed of extraordinary light, they are called as negative crystals. They are known as negative crystals. So now try to understand, if you are having a point source, if you are having a point source that is placed in calcite crystal, negative crystal. So here this is x-axis, this is y-axis, and I'm saying this x-axis is representing optic axis. This is representing optic axis. Optic axis like this. Now there is a point source here at this point O. I'm saying point source is here at this point O. Now, for O ray, when light will emerge from here, so two wavefronts will emerge. One will be corresponding to O ray. So what type of O ray wavefront will be? That will be spherical. Another wavefront will be corresponding to E ray, that will be ellipsoidal. So along the optic axis, their shapes are different. These lights, they are traveling with different speeds, but along optic axis, they are traveling equal distances in equal time. Their speeds are same. So what type for this, you can say, for O ray, you're going to have this type of wavefront, spherical wavefront. But this time, in general, VO is less than VE. So you will find out that along the optic axis, both are going to touch each other. And in other directions, in other than optic axis, in all other possible directions, E ray, that is going to move faster. So O ray will left behind. So it is like this. So this is what? This is E ray. This is the wavefront corresponding to E ray. This is the wavefront corresponding to O ray. E ray and O ray. So please write here. In case of negative crystals, in case of negative crystals, in case of negative crystals, spherical wavefront of ordinary light, spherical wavefront of the ordinary light, in case of negative crystals, please write, in case of negative crystals, spherical wavefront corresponding to ordinary light will lie spherical wavefront corresponding to ordinary light will lie inside the spherical wavefronts, inside the spherical wavefront, inside the spherical wavefront.
Sir, ellipsoidal or spherical, sir?
In case of negative crystal, spherical wavefront corresponding to ordinary light will lie inside the ellipsoidal wavefront corresponding to ellipsoidal wavefront corresponding to E ray will lie inside the ellipsoidal wavefront corresponding to E ray corresponding to E ray corresponding to E rays. You can look here. This sphere is inside this ellipsoid. Here, in case of positive crystal, this ellipsoid is inside the sphere. So in this way, you can differentiate between these two type of crystals. So these doubly refracting crystals, they are of two types: positive crystal and negative crystals. Positive crystals and negative crystals. Is it clear up to this point?
Yes, sir.
Good.
Yes.
Yes, beta, please. Please note it down quickly. Now, on the basis of this type of property, that unpolarized light, when it passes through a doubly refracting medium, it produces two lights. ठीक है, two plane polarized light. One is ordinary and another is extraordinary. ठीक है, one can design, ठीक है, one can design a optical instrument that is called as Nicol prism. So what is Nicol prism? Nicol prism is an optical device with the help of which we can produce plane polarized light from an unpolarized light. So if you are having unpolarized light that is passed through a Nicol prism, you can produce the plane polarized light. So next is Nicol prism. So next is Nicol prism. So what is Nicol prism? It is an optical device. You can say this is an optical device that is used to produce plane polarized light from unpolarized light. UPL. UPL means unpolarized light. UPL means unpolarized light. PPL means plane polarized light. Plane polarized light. ठीक है? So this Nicol prism, it is made up of calcite crystal. First thing, calcite crystal. Here, I'm going to show you the principal section of the calcite crystal. So what you are having here, we are having a calcite crystal that is cut in this way. This length is roughly 3 times. This width, you can say, that is 1 time. So length is to width, that is in the ratio of 3:1. Okay, so this type of crystal you are having. So you are having length, you cut it in this way. Length is to width or width, you can say breadth. Yeah, width is roughly 3:1 beta. Why you're using this 3:1, I'm going to tell you. So this type of crystal we are choosing. What you have to do, you have to cut it diagonally. What you are going to do, you will cut it diagonally. So what you have done here, you cut it like this. So now you are having this type of two pieces. Try to understand. So one is like this. One piece is like this. Another piece is this. So you have cut this crystal in this way. Now what do you do? Okay, here in between these two, you paste a cement that is called as Canada balsam. Canada balsam is a cement that is used to attach these two quartz crystals together. So what you do, you place here, okay, a cement that is called as Canada balsam. So what you do here, you a small layer, very thin layer of Canada balsam. So here in between these two, what you do, this is Canada balsam. Canada balsam. And this is a cement. This is a cement, type of cement. Now, with the help of this cement, you attach these two parts again together. So what you are having here, you are having this type of structure. So first you cut and then you have added them together. with the help of Canada balsam. So here you are having this Canada balsam. This is Canada balsam layer between these two parts. Okay? So this is calcite, this is calcite. In between them, there is a layer sandwiched between these two parts. So in between these two parts, you have sandwiched a layer that is known as Canada balsam. Okay? So this type of structure you have created, and this is known as Nicol prism. How it works, I'm going to tell you. So first try to understand here the refractive index. So refractive index of extraordinary light in this direction, I'm talking about this direction roughly. In this direction, this is 1.48. Okay? For Canada balsam, this is I think 1.52. And for ordinary light, this is 1.6. I just check it. How much is it is 1.65. This will be 1 point. This is 1.55 and 65. Try to understand. This is. So in this direction, I'm talking a particular direction. Try to understand this calcite crystal. This is a doubly refracting crystal. It will have different refractive indices for E ray in different directions. But I'm talking about this direction. When you have designed this, so in this direction, refractive index of extraordinary light is like this. So you can, in this direction, if you look at mu E, refractive index of E ray, that is less as compared to the refractive index of Canada balsam. But if you look at mu O, that is greater than mu CB. So refractive index of this Canada balsam is in between these two. Okay? In between these two. Another important aspect is this this Canada balsam, this cement, it is not a doubly refracting medium. Calcite is a doubly refracting medium, but Canada balsam, this is not a doubly refracting medium. Here in Canada balsam region, O ray and E ray, they will be same. ठीक है? O ray and E ray, they are having their existences as O ray and E ray only in doubly refracting medium. In ordinary medium, they will be same. ठीक है ना? In ordinary medium, both the O ray and E ray, they will behave. ठीक है? They are simple lights. ठीक है? Their polarization may be different, but otherwise they will be same. They have same speed in all possible direction. If you created O ray and E ray, and then you pass these created O ray and E ray through a medium which is not doubly refracting, so they will behave as ordinary lights. Okay, they will be polarized, perpendicularly polarized, but they will behave ordinary as ordinary light. Speed will be same. So try to understand here. This Canada balsam is not a doubly refracting medium, not a doubly refracting medium. This is not a doubly refractive medium. This is. Okay? So now we are having this structure. One by one, I'm going to explain you everything here. This is calcite crystal. This is doubly refracting. So this is a doubly refracting medium. Now what you do, basically you are going to launch from here, you are going to launch a unpolarized light. So what you are going to do here, from here you are going to launch a unpolarized light I'm talking about. So this unpolarized light you have launched. This is unpolarized light. Okay, that is launched by you. Okay, you have launched this unpolarized light through this. Now, when it will enter into this is doubly refracting medium. So when it will pass through it, try to understand. I'm not making very proper diagram, but so try to understand it will split into two. Okay, one part is this. Okay, and this is what type of part here? these electric vectors, ठीक है, these electric vectors, they are parallel to this plane, parallel to the principal section. So what I'm showing you here, this is whatever you are looking in on the board, that is principal section. Remember this, principal section of Nicol prism. Nicol prism. So ordinary light, this unpolarized light, it is splits into two parts. One part will be this. It will travel as O ray and it will pass through this Nicol prism. It will come out like this. There will be some angle of refractions also here. Okay, so I'm not interested at this time what will be the angle of refraction in that. And from here, what you are getting here. This is E ray. So these components, these electric vectors, they are behaving like the E ray component, extraordinary ray, because these electric vectors, they are parallel to the principal section. What you are getting here, here you are getting E ray. What you are getting here, you are getting E ray here. This is E ray, beta. So what you are having here, you are having E ray, extraordinary ray. So here this is plane polarized light. From this side, what you are getting plane polarized light. That is okay. That is okay. Now, what is happening to other? This is another one. This is the second. This is the second refracted light. This is the second refracted light. Its electric vectors, they will be perpendicular to the principal section. Try to understand it. Try to understand this. And if you are launching, try to understand this length is 3. This width, this is 1. 3:1 ratio, and we are launching this light nearly parallel to this base. So try to understand, if I draw a normal here, this angle will be quite large. Okay, why we are launching it parallel to the base and why we are taking it 3:1. Try to understand, due to this region, this is a diagonal plane. This is a diagonal plane, and when you are launching this light and this ordinary ray, these dot components, when they are going to strike here, this angle, it will be more than polarization angle or Brewster angle. Oh, so sorry. This will be not polar. Sorry. This will be more than critical angle. Sorry, beta. Theta C. That is theta C. What is the meaning of this critical angle? Okay. What is the meaning of this critical angle? Try to understand. So before moving further, before further explaining, try to understand here. Suppose this is a denser medium. This is a denser medium, beta. And this is rarer medium. And I'm saying light is traveling in the denser medium. Okay, light is traveling in the denser medium. So this is N1. And light is entering into the rarer medium. This is N2. N2. So what happens when light travels from the denser medium to the rarer medium? This light, ठीक है ना, it will bend away from the normal. So what will happen if a light is incident over this interface? So what you are going to have, this is the normal, and because it is entering into the rarer medium, it will move like this. It will move like this. If you further increase this angle of incidence, if you increase this angle of incidence here like this, what will happen? It will further move away from the normal. And there will be a particular angle, then you will find out a particular angle. Okay, that is known as critical angle. When at this angle, you are going to launch the light from the denser medium on the rarer medium, then you will find out here. This will be the refracted light parallel to the surface. This will be the parallel. So this is the theta c is the angle. Try to understand, theta is c is the incident angle for the light which is moving from denser to rarer medium, at which if light is launched, then angle of refraction, this angle of refraction, this becomes 90 degree. 90 degree. Now, if you launch the light at an angle greater than theta c. Try to understand, if you are launching a light at an angle that is greater than, so if this theta is greater than theta c, what will happen? You will have only this part. You are going to have only reflected part. There will be no transmitted part here. There will not be any transmitted part, only reflected part will be there. This phenomena where all the incident light is reflected back into the same medium, that is called as total internal reflection. You call it as total internal reflection. Total internal reflection. Internal reflection. What do you call it? You call it as total internal reflection. In total internal reflection, first condition is light should travel from denser to rarer medium so that light can bend away from the normal. First condition is this. Second is when light is incident at an angle theta c, then refracted light, ठीक है ना, it will travel at an angle for which r is equal to 90 degree. So the direction of this light, it will make an angle 90 degree with the normal. So when light is going to be launched at an angle theta greater than theta c, you will have only the reflected part of the light. There will not be transmitted here. Both parts were there. ठीक है ना? In this case, in another cases, both parts were there. Reflected part was there, refracted part was there. But in this case, if angle of incidence is greater than theta c, then only this part will be there. What will be this angle? How can you calculate this angle? Try to understand. This is first medium. So I write n1. We call this angle as angle of incidence, and this is, we have written it as theta c. So angle of incidence is theta c in the first medium. This will be equal to refractive index in the second medium and angle of refraction, that is 90 degree here. Sine 90 is 1, so sine theta c, that will be equal to n2 upon n1. So here, in this way, you can find out if n1 and n2, they are known to you, then you can find out sine theta c. ठीक है, theta c value you can find out. So here, what is important here? Light should travel from denser to rarer medium. So this condition is matched here. Try to understand these two conditions. Here, first for E ray, first look for E ray. E ray was traveling in quartz. So refractive index of E ray is less as compared to this Canada balsam. So for E ray, there will not be any TIR. There will not be any TIR because light is first, this E ray is first traveling in calcite crystal, and in calcite crystal refractive index of extraordinary ray is 1.48. When it strikes this Canada balsam, whose refractive index is 1.55, so that is greater. So first medium is rarer medium, Canada balsam is a denser medium. So light is traveling for E ray. If you look at for E ray, here I write E ray, how E ray are traveling? E ray, they are traveling from rarer, rarer medium to the denser medium. Denser medium. Who is denser medium? Canada balsam. Who is the rarer medium? That is this calcite. Calcite. So there is no possibility of TIR. So no TIR take place. No TIR take place. But if you look at E ray, sorry, ordinary ray, O ray, then for O ray refractive index is 1.65. So here in this medium, when this O ray is traveling, when O ray, these components, perpendicular components of electric vectors, they are propagating here in this medium. Refractive index is 1.65. When they strike over this Canada balsam, ठीक है, when they strike over this Canada balsam, its refractive index is 1.55. So here in this case, light is traveling in a denser medium and it is striking on a rarer medium. So for E ray, for O ray, for O ray, in case of O ray, light is traveling from denser to rarer medium. Who is rarer here? Canada balsam. And here this is calcite. This is calcite crystal. So from calcite to Canada balsam here. So here in this case TIR is possible. So in case of ore, TIR is possible. TIR is possible. This is possible. So because we are launching this light parallel to the base, so try to understand this angle will be sufficiently large as compared to this theta c. तो ये बेटा थीटा सी से ज्यादा ही आएगा. दिस वैल्यू विल कम आउट टू बी ग्रेटर देन थीटा सी. ठीक है, तो ये थीटा सी से ज्यादा आएगा. So what will happen here? Light will undergo TIR. So it will move like this. It will undergo TIR. And this is ordinary light. Ore. So ore undergo TIR and it will be side. ठीक है ना? It will pass through the side and on the other side of the Nicol prism, only E ray will pass. What you do here, that is very simple here. On this side, you can paste a black paper or some absorbing medium. Here you can have some absorbing medium layer or simply you can have black paper. So this ordinary light that will be absorbed by this. So what will happen to the ore? Ore will be absorbed. ठीक है, ore will be absorbed by this absorbing medium here, layer of absorbing medium. So what is happening now? Try to understand UPL is incident on this side and on this side we are getting E ray only. So through the Nicol prism E ray is passing. So E ray will emerge as plane polarized light from the other side. What will be the direction of electric vector? Electric vector will be parallel to the principal section of this Nicol prism. So these E ray electric vectors, they will be parallel. So in this way, you can produce plane polarized light from the unpolarized light. So one can produce plane polarized light from the unpolarized light with the help of this Nicol prism. If they ask you what will be the critical angle here, so that is very simple. Sine theta c. Sine theta c will be how much? I have given you the formula here. That will be n2 by n1. Second medium refractive index divided by first medium refractive index. So this will be second medium here is Canada balsam. Canada balsam. So this is 1.55. 1.55 divided by 1.65. 65. ठीक है, so from here you can find out the exact value of theta c. ठीक है, you can with the help of a calculator you can find out. Now we were making it certain that light, this ordinary light, it should strike at an angle greater than theta c. So this angle theta is actually greater than theta c here. So for this purpose we have designed this Nicol prism. Its length is quite large. Its width is small. Okay, only one part as compared to three part of length. So if you cut it diagonally, then what you will find out that for this incident unpolarized light, that is incident parallel to the base, nearly parallel to the base. Here angle of incidence for ordinary light, it will always be greater than this critical angle. So that's why TIR, O ray will undergo TIR. It will be absorbed from the sides and extraordinary light, this will pass through it. So in this way, plane polarized light can be produced from the unpolarized light. Okay? In this way you can produce. So this is Nicol prism. So this is the working of Nicol. I have given you the basic aspects, physical aspects on the basis of which this Nicol prism work. Now, here I am showing you, this is Nicol prism. How you show in journal Nicol? In journal, I'm going to show you Nicol like this. So what you are observing here, this is principal section. section of nickel. I call this angle as theta equal to 0. What I'm calling it, I'm calling it at 0 degree. ठीक है? I'm calling this situation of the Nicol prism at theta equal to 0. Now, unpolarized light is incident over it. ठीक है? This is unpolarized light is incident over it. From here, this is E ray. It will pass through it and it will move like this. And angles will be there, but I'm just showing like this. So what you are getting here, this is E ray. E ray. So when an unpolarized light is incident on a Nicol prism, only the electric field components which are parallel to the principal section, they are emerging out. And the components which are perpendicular to this, which are like this, the component electric vector components which are perpendicular like this, which we call ordinary light, they are absorbed here. ठीक है ना? They are absorbed sidewards. Sideward. So if intensity of unpolarized light here is I naught, what will be the intensity here of this? That will be I1, and how much it will be? Half of this. So this is very similar to polarizer. So what here, this Nicol prism is acting here. Nicol, it is acting as a Nicol prism. Here it is acting as a polarizer. So what you are observing here, you are observing here that from unpolarized light, you are getting plane polarized light. And this is called as polarizer. What polarizer does? It converts unpolarized light into plane polarized light. Okay? So here, this Nicol is acting as a polarizer. Polarizer. This is Nicol 1. I call it as Nicol 1. N1, you can also write it as N1. Okay? Now what I do, I place another Nicol prism here. I place another Nicol prism here. Identical Nicol I am using. I am calling it as N2 or Nicol 2. And I place this Nicol prism in such a way that principal section of this and this, they are parallel. So what I'm saying, the principal section of this and this, they are parallel. So this is Nicol 2 and its principal section is also lying in the board, along the board. So when these vectors, they are going to enter here, these electric vectors, they will be parallel to what will be, they will be parallel to the principal section. So here there will be no overlay. There will be no double refraction here. Try to understand. Because these electric vectors which are entering into this Nicol, they are parallel to principal section. So this incident light here, this is acting as E ray. And on this side, you will get E ray only. Plane polarized light you are going to get here. And this will be plane polarized light. Okay, intensity how much? I2, that will be I naught by 2. So maximum intensity you can say. This will be maximum intensity. Maximum intensity. Okay? And here this is Nicol 2. Nicol 2. It is also at theta 2 is also 0. So here theta 1 I can write. So basically here both the principal sections, they are parallel to each other. So whatever E ray, whatever plane polarized light is emerged here, its electric vector will also remain parallel to the principal section and it will come out of this second Nicol as plane polarized light. But now what you do, okay, this time you rotate this Nicol by 90 degree. What you do, you rotate this Nicol by 90 degree. Okay, so what I did here in second case, I rotated this Nicol by 90 degree. Uh, Actually, this. So what I did here, I rotated this by 90 degrees. So try to understand rotated Nicol is shown like this. We generally show like this. Rotating Nicol is this type of. ठीक है? This will be this type of rotating. So what is happening here? This was the polarizer. This is the polarizer here. This is Nicol 1. Both are identical. This is Nicol 1 N1. Here theta 1 is 0 degree. Here unpolarized light was incident. This was unpolarized light. Here unpolarized light was there. So E ray that passes through it. This is E ray. So here this is E ray. This is plane polarized light. Its electric vectors are parallel to the principal section here. So these electric component they will enter into this. Now this is Nicol 2. Try to understand this is Nicol 2. But this time its principal section is perpendicular to the board. Its principal section is perpendicular. You have rotated this Nicol by 90 degree. So theta 2 here is 90 degree. So try to understand if principal section is perpendicular to the board, then these components, ठीक है ना? These components they will perpendicular to, suppose that is this plane. This plane is Nicol. This plane is the Nicol's principal section. So these electric vectors, they will become perpendicular to this. So try to understand as they enter inside, they are perpendicular to the principal section. They are perpendicular to the principal, and what they undergo, they will undergo TIR. So they are acting as O ray here. O ray. This was E ray here. This light was behaving as E ray here. But here, these components, they are now perpendicular to the principal section. So that's why they are behaving. Electric components perpendicular to principal section, they are ordinary light electric components. So this is O ray here. So this is here. This is side reflected. It will be absorbed from the sides, and here no light will be there. ठीक है? Here intensity will be 0. Intensity will be 0. ठीक है? So here, so what you are observing when theta is 0 or theta will be 180. So what you are going, please note it down quickly.
Sir, in previous slide, you have means done means say the black portion is to absorb the ore, right?
हाँ, that is for O ray. That is also here. ठीक है ना? That is also. So here on the side there will be a absorbing layer that will absorb this ordinary ray. ठीक है? Whatever light is passing through the side of this Nicol, that will be absorbed. Only the light that is crossing this Nicol, ठीक है, that is transmitting through this Nicol and it is coming out from this side, that will pass. That you can observe. ठीक है? So whatever light is crossing through these sides of this Nicol, that will be absorbed. Is it clear? So
Yes.
good. So now, so here try to understand. This is Nicol 1 that is acting as a polarizer. That is acting as a polarizer. What it does? Light is incident. Unpolarized light. Unpolarized light is incident. From here I am getting plane polarized light. Its electric vector are parallel to its principal section. So this is plane polarized light. So you're calling it as polarizer. Nicol 1. Now, what you do? There is second Nicol here. and we can rotate this Nicol. This is on the stand, and on this stand we can rotate it. So what we can do here, we can rotate this Nicol. So we can rotate this Nicol about this axis. This is the axis. Okay, this is the axis. About this you can rotate. What you are going to find out here, you will find out when here angle for this is theta1, angle for this is theta2, and I'm saying delta theta. Angle between the principal, what is delta theta? That is theta1 minus theta2 and mod of this. Okay? Mod of this. This is the angle between the principal sections of two Nicol. What is delta theta? Delta theta is the angle between the principal sections of two Nicol. You can write, please. Delta theta is the angle between the principal sections of two Nicols. Try to understand when this angle is 0 or a 180 degree. Then here intensity I will be maximum. Will be maximum. If unpolarized light is incident on the Nicol, you are passing it through this and you are rotating it. So when angle between these two is 0 or 180 degree, then intensity will be maximum. Second, if delta theta is equal to 90 degree or 270 degree, it means principal section 90 degree and at 90 degree and at 270 degree, principal section of two Nicols will be perpendicular. One will be like this, another will be like this. So in that case, intensity will become 0. So in this case, what will be the intensity? Intensity will be 0, or this is minimum intensity. So if you are rotating the Nicol here, try to understand what type of light is this. This is plane polarized light. If you are rotating the Nicol, and in one rotation, during one rotation, 2 times intensity is becoming maximum and 2 times intensity is becoming minimum. 2 time intensity is becoming maximum and 2 time intensity is becoming minimum. It means that this incident light which is falling on this Nicol, that is plane polarized light. So here this Nicol 2, this can be used as an analyzer. So how you are using as an analyzer, try to understand if this is your second Nicol or you are having a Nicol prism and an incident light here, I don't know, this is unknown light. This is unknown light. Unknown light. And here on this side you are having detector. You are getting intensity. And what type of intensity you are getting? In one rotation, 2 maxima and 2 minima. And 2 minima of intensity 0. You're getting this. It means, so what this is going to tell you, if you are getting this type of result, okay, on rotation, during one rotation, if you are getting 2 maxima and 2 minima with 0 intensity, it means this is, you are sure that incident light is plane polarized light. So this is a test for plane polarized light also. So if a plane polarized light is passed through a rotating Nicol, then intensity will become maximum 2 times and 2 times it will become 0. If this result you are getting with the help of a rotating Nicol, it means your unknown light, your incident light, your unknown light, this is plane polarized light. This is plane polarized light. This unknown light is plane polarized light. Is it clear?
Yes, sir.
Yes, sir.
ठीक है बेटा. So in the next class I will explain you how with the help of a plane polarized light you can get circular polarized light, elliptically polarized light. What is the meaning of left circular, right circular, left elliptical, right elliptical? So all these aspects we are going to discuss from the next class. So up to this point, I have discussed only two type of lights, unpolarized and plane polarized. But in the next class, we will find out circularly polarized light and elliptically polarized light. ठीक है? Okay, beta.
Sir,
Yes, beta, please.
can you show me the second slide?
Yes, beta, I will show you all the slides. Just
The next one, sir.
second, just 1 second. This is second one.
The next one, sir.
This one.
Yes, sir. I have a doubt.
Please tell.
Sir, in the previous class, you told that when a plane polarized light is passed through a polarizer, the intensity will be I naught cos square theta.
Yes, it will be. Yes, it will
I
be.
naught cos square, sir.
Try to.
But here in the Nicol 2, after that the I2 is I naught by 2. Why, sir?
Okay. Here, look at angle theta. This is delta theta. So what will be the intensity on this side? Try to understand I2. I2 will be I1 cos square. I'm writing it as delta theta. In place of theta, I'm writing it as delta theta. Okay? So what is here delta theta? This is 0, this is 0. So in this case, delta theta is 0. So cos square 0, that will be 1. So I2 will be I1.
Oh, okay, sir. Thank you, sir.
Here, if you look at delta theta, that is theta 2 minus theta 1, that is 90 degree. So what will be the intensity here, I2? That will be I1 cos square 0. So no, cos square 90. Cos square 90 degree, you are aware that is 0, so that's why 0. Okay? So here I have shown you
Yes,
the
sir.
cases for theta equal to 0 and theta equal to 90. Other than this, if angle between two principal section is theta, 30 degree, 40 degree, 60 degree like this, then here intensity will be I2 will be I1 cos, suppose 30 is the angle, this angle is 30. Suppose angle between the principal section of this and this is 30 degree, then this will be I1 cos square 30 degree. Okay? That will be cos
Okay,
square
sir.
30 degree. Okay. So now please
Sir?
save. Oh, yes, Peter.
So why in Nicol prism we are using a black absorbing surface to absorb O ray? Why it is
Because
not?
black color objects, they are very good absorber. They are very good
So
emitter.
why are we observing the O ray, sir?
Because with the help of Nicol prism, what is our purpose? Why we are designing this optical instrument? We want to produce a plane polarized light. So that's why I just want only one type of plane polarized light. Either it is O ray and E ray. Okay, but it should be only one plane polarized light. So that's why out of the two refracted rays, one is absorbed from the sides, another is going to pass through it. So you are getting here unpolarized light is incident, on this side you are getting plane polarized light. So we are not concerned with O ray and E ray. My objective here is just to find out the E ray only. ठीक है, मुझे E ray चाहिए, plane polarized चाहिए, not E ray. I want plane polarized light. So it doesn't matter it is E ray or O ray here. I want plane polarized light. This is first objective. Later on, when we have to rotate the plane of vibration, we will think about other aspect. But right now, we are just want to produce plane polarized light whose electric vector are they are confining in a plane. So this is here. So another is absorbed. So only one type of plane polarized light we are having. So our objective is fulfilled in this way. Later on, we will
Okay.
further discuss. If you are not having Nicol prism, you are having double refracting crystal. You will get here. You can get both type of plane polarized, E ray as well as O ray. Okay, so we can also get that. later on I will discuss in the last.
Okay, sir. Thank you, sir.
Welcome, beta. So this is the first slide. Please save. This is the first one. This is second. Third. This is fourth. This is, I have explained you something, fifth one. This is sixth one.
The first slide again.
Which one, beta?
First slide.
First slide. This is the first one. Oh, sorry. This is the first one.
Okay, sir.
Okay, beta.
Thank you, sir.
Welcome, beta. Okay, beta.
Thank you, sir.
Thank you, sir.
Welcome,
Thank you,
beta.
sir.
Welcome, beta.